Hey, good morning to all of you. Welcome to the Center for Bioplastics and Biocomposites fourth webinar in a recurring series on sustainable materials. These webinars will take place every few months and highlight the work of the 4 sites that are part of the Center for Bioplastics and Biocomposites, which is a NSF IUCRC, and the 4 institutions that are collaborating within the center are North Dakota State University, Iowa State University, Washington State University, and University of Georgia. And you could find further information about the center at CB2center.org. At this moment, I would ask all of you to please mute yourself if you're not. And I will introduce first to our speaker. And my name is Vikram Yadama. I am the Center for Bioplastics and Biocomposites co-director, site director at Washington State University. So today we have an excellent speaker, Dr. Chad Ulven, who will be presenting about opportunities and challenges for natural fiber composites. Chad is a professor of mechanical engineering at North Dakota State University and Chief Technology Officer at C2 Renew, Inc. He has been involved in the research of polymer matrix composites for various commercial and defense applications for the past 20 years and has co-authored 6 book chapters, 8 journal articles, and over 100 conference papers in this area of polymer matrix composites. He has also co-authored 5 patent applications, of which 4 of them have have been awarded, and 2 of them have been have spun out into companies C2 Renew Inc. and C2 Sensor Corp. With that, I would like Chad Ulven I would like to welcome Chad Ulven and present the webinar. Thank you.
Thank you very much, Vic. Good morning, everyone. And as Vic mentioned, if everyone could mute themselves, I plan to present for about 35-40 minutes, and then we'll open it up for questions at that point. Both if you feel comfortable unmuting yourself and speaking, but then also in the chat. So we'll do that later on in the presentation. So can everyone see my screen all right?
Yes, thank you.
All right, thanks, Vic. So as Vic mentioned, I'm both a professor in mechanical engineering at North Dakota State University, as well as a Chief Technology Officer of C2 Renew, which was founded in 2012. And so I kind of consider myself in a unique position where I see things from a research perspective. What are the challenges? What are the opportunities for in-depth research at the university? But then also what is possible on the commercial facing side? Who can these materials, when developed properly, serve? What kind of customers, whether it's in industrial applications or in consumer facing products? C2 Renew has offered a lot of different biocomposite products in the market. And so again, I kind of consider myself in a unique position that I can see both sides. Just want to throw it out there, people ask me all the time, what is possible for natural fibers and biocomposites? And here you can just see a whole host of different potential applications. We have cell phone covers, we have bicycle frames, we have insulation batting, we have erosion control logs, we have insulated bricks, we have tennis rackets, guitars, the list goes on, and people always ask me, well, what is possible? And all of the above. There's a lot of opportunities for these applications, specifically when you look at bast fibers such as flax, hemp, jute, calf. You can use the woody core for a lot of different applications, and you can use the fiber for a lot of different applications. Similarly, people ask me all the time, well, what type of plastics can we make from these materials? And there's a wide variety of different plastics that can be made, either forming epoxy or acrylic type of thermosetting resins from the vegetable oils. You can break down the cellulose into their simple sugars and build them back up as, say, cellulose acetate type of thermoplastics or polylactic acid type thermoplastics. There's a wide variety of different ways you can utilize this plant. And so, again, my answer is always yes. There's a ton of different plastics that can be made from these materials. But at the end of the day, we have to decide what is truly sustainable, what is going to have relatively low environmental impact, what is going to be beneficial economically, what is going to be beneficial to the people handling these materials in these processing facilities, manufacturing facilities. Only then, when you start to assess all of those aspects, are we going to be able to determine what is sustainable and what is not moving forward. And I'm sure you're all very, very much familiar with concerns about the amount of plastic that has entered into our waterways. There was this Ellen MacArthur Foundation study that was done long ago, or a few years ago, to predict what type of volume of plastic might be in the ocean in coming years. Also, we've seen estimates of running out of landfill space. Estimates of the U.S. will be on pace to run out of room in landfills by 2035, which is not too far off in the horizon. And so when we look at how to develop materials and what is truly sustainable, our group really focuses on the kind of three capitals of natural capital, what our planet offers us, manufactured and financial capital, the prosperity, the human and social capital, our people, and one thought is where these three intersect is where you can truly find some sustainable materials, sustainable technology, something that can have very low impact on the environment, yet be financially sound and make money and sustain people in terms of their work-life balance, in their prosperity and their development as humans. That intersection is where we find sustainable material development. And we do a lot of the analysis of any material that we develop. We look at both the LCA life cycle assessment as well as the techno-economic analysis to help determine, hey, are we meeting this sustainability target right in the middle there, or are we off? Are we off base? And so these are some of the tools that we've been utilizing with colleagues to try and determine when we're developing new materials if we're meeting this mark. So our research approach at North Dakota State University over the past decade really has been focused on working as a land-grant university, working with our agronomists, our plant breeders, and looking at what's available out in the fields. What can we break down into, say, proteins or starches, stripping the natural fibers from the bark of a stalk, utilizing the woody core. Is there alternative uses for the vegetable oil that one can convert into different plastics and use to manufacture a wide variety of composites that ultimately will hopefully end up on commercial applications, whether it's farm equipment, automotive, consumer-facing products, the list goes on and on. And for several years, we had our Sustainable Materials Science Center that was funded through NSF EPSCoR for 6 years. And we're just coming off of that. And really now, since we've been able to develop several different materials utilizing this approach, we're starting to look at how can we then implement those through industrial applications by working through CB2, which is, again, this webinar is part of. I kind of break the development of different biocomposite materials down into 3 project areas that I've been involved with over the years. Short natural fiber, and this can be thought of as mainly fillers in different types of plastics, from say hemp, flax, sunflower hull, oat hull. We've analyzed and assessed many different types of these agricultural byproducts as fillers or short fiber reinforcement. Then there's the category of long natural fiber, where you start to see fibers and utilize fibers with aspect ratios of greater than 2,000, that length to diameter. And this would be also your flax, but the fiber comes from the outer kind of bark of your stalk. Similarly with hemp, and I mentioned earlier, canaf, jute are other examples of bast fibers. But there are also long fibers available in grasses, certain grasses, giant macranthus, blue stem from around here, that one can utilize as reinforcements. And then I work very closely with colleagues on biopolymer development, from both NDSU as well as some of the other participating universities in CB2, such as Iowa State, University of Georgia, where they're developing polymers from vegetable oils, proteins, starches, all in the same vein of trying to develop more environmentally friendly or more sustainable types of polymeric resins for coatings, for composites, for a wide variety of different applications. What makes natural fibers, bast natural fibers in particular, very attractive is looking at their physical properties. Flax, hemp, jute, as you see on this chart, have some outstanding tensile strength as well as stiffness or Young's modulus in comparison or as compared to things like glass fiber, especially when you account for their density, because their density is about half that of fiberglass, traditional fiberglass that's used in a lot of composite manufacturing applications. And so we have a huge opportunity here to utilize some of these materials in advanced composites. However, one of the most critical areas is the breakdown of the bast plant. How do you take the straw that's coming off the field after the seeds have been harvested? How do you take that straw and appropriately break it down for different applications? And that process of separating the fiber from the woody core is known as decortication. And there are many different ways to decorticate natural fibers from that woody core in the stalk. Some of them a little more aggressive or harsh to the fiber in terms of breaking it down, maybe creating some kinks, maybe shortening the length. Whereas other types of decortication processes really handle the stalk in a more gentle way so that they can extract the fibers and allow them to remain intact. And there's a lot of different, especially in the US, there's a lot of different groups that are looking at putting decortication facilities up, especially now with hemp being able to grow in the US, and look at how efficiencies can be gained when you choose certain types of decortication processes. But again, much of that decision is made on where is the application. Is it in textiles or is it in erosion control blankets? Because in my opinion, you're going to utilize a very different decortication process. Another factor that I haven't mentioned yet is the process of retting. And retting can be done in a couple different ways. Either natural dew retting is what they refer to this as, where the stalk is left out in the field to naturally ret and break down due to the humidity in the environment and time, basically. Another way is to artificially water ret, which is complicated in that it takes a large body of water to soak these stalks in. And then always the question is what do you do with that? What do you do with that wastewater after it's been used to artificially ret, excuse me, those stalks and separate them? And then there's been a lot of work done on enzymatic retting, which is again a very controlled but now a little more expensive process because you're introducing another chemical to the process. And the constituents of bast fibers do change based on variety and growing conditions. And so what I'm finding more and more useful is when people report data on different types of fiber that have been harvested and tested. It's much more useful if we understand things like if any lignin or cellulose content, pectin, hemicellulose content has been measured to report those, along with the method of retting and some sort of could be, more of a visual assessment or organoleptic type of assessment of the quality of that fiber. And just to give some perspective of and background information on a particular fiber, because all of these pieces of information become relevant and become important when you start thinking about where can I use this fiber? Is it of a higher quality that I can potentially utilize it in an automotive application? Or is it of a quality where maybe I need to think about it in a geomat type of architecture or like I mentioned earlier, erosion control type of blanket where the quality of the fiber doesn't need to be as high in those applications. But by and large, the role of the natural fiber in biocomposites, there's several advantages, being lighter weight, lower dermal abrasion. If you've ever handled natural fiber versus fiberglass, there's a stark contrast there, and that comes from health and safety of the worker, the handler in the manufacturing facility. Reduction in energy consumption, the types of high energy and melt temperatures that are required to make glass fiber versus natural fiber. Although there is a good argument of the the fuel that's used in the tractor and the equipment that's utilized out in the field, and you only see that or only realize that when you go through a full life cycle analysis or techno-economic analysis to identify those inputs, such as the fuel that the tractors use as they're harvesting the fiber versus melting down soda lime to make fiberglass. Better vibration dampening capabilities, better insulation and sound absorption properties, and I'll get to that in a second. Better degradation when service life is exhausted. However, there is some concern, well, if these materials degrade so much more readily than, say, fiberglass, do we have to be concerned when we try and make a fender on our automobile out of them? And there's ways to protect that, and that really hinges on or is dependent upon the matrix or the type of plastic that you use to encompass those fibers to protect them. And then overall, the goal, I think, in all of this is to reduce our dependency on petroleum-based products and the high energy consumption that's needed to make things like fiberglass is the ultimate goal. However, natural fibers, just like anything, have their cons. The challenges are they're extremely hydrophilic. They take on moisture, low degradation temperature. Maximum temperatures that they can be exposed to for long periods of time is around 180 degrees centigrade before they start breaking down. And their properties are very variable from the standpoint of, again, different types of varieties, the climate in which they're grown, the soil conditions in which they're grown, and how long they're grown before they're harvested all affect their properties and give that variability in performance. A lot of the dampening and insulative properties from natural fibers stems from their hierarchical structure. They're very complex structured fibers with the cellulose as the backbone, and your pectins and your lignins kind of adhering them all together in this multi-step fashion as shown here or illustrated here. The strength and the stiffness of your fiber really comes from that secondary wall and how the cellulose, crystalline cellulose, is oriented in that secondary wall. And what we found and others have studied as well is that angle in which the cellulose grows during the growth period really determines that strength. If you've got a greater angle off axis to the fiber, you have a much lower modulus or lower stiffness fiber, as if you'd have the cellulose constituents growing along the axis of the fiber as it's being grown. I talked a little bit already about the time in which you should harvest the fiber, the optimal time. And depending upon the variety and the growing conditions and the time of year, sometimes you can have natural fibers that have a very closed, uniform cross-section, whereas later on in the growth process, they develop what's known as a centered lumen. And that lumen can be a source of weakness in the fiber, especially if it gets too big and you cannot penetrate the lumen with resin unless you use a high type of vacuum in order to fully infiltrate the center lumen and fully wet it out. And so again, just to point out that even when you harvest the fibers is important if you're trying to grow them for certain applications, whether it's automotive or aerospace grade type of composites versus something like an erosion blanket or a geotextile where the performance requirements might not be as high. In my group, we've tried several different physical treatments, fiber surface treatments, both physical and chemical. Physical treatments that we've tried or looked at and assessed, simple mechanical, calendaring, rolling, swaging, combing for long periods of time can have some decent effect on separating the fibers, cleaning them of those waxes and pectins. However, they cause some breakdown of the length of the fiber, and so it's kind of again a trade-off. Solvent extraction. We've tried electric discharge, both plasma type of treatments, which have some effect. They're not long lasting, but they can excite that surface so that you can apply your resin or your coating and have a better inherent bond between your resin and your fiber. Some thermal treatments to basically decompose some of those lower molecular weight natural polymers, the pectins, the waxes, and so we've tried some autoclave treatments. Steam explosion is another route. Chemical treatments, we've tried, there's various alkaline treatments that can be done, coupling agents such as silanes that are used for synthetic fibers, carbon fibers, glass fibers, bleaching, enzyme, peroxide, the list goes on and on. But what I want to emphasize here is in most of our work, many of these treatments only give you a gain of strength or modulus in 10, maybe 15% if you're lucky. And so again, it comes down to that balance of these utilizing some of these expensive chemicals, what to do with the waste for the minimal gain that you might get in the properties or the performance. Is that sustainable? And those are the types of questions that need to be asked and answered through your life cycle analysis. Some study that we've done on the natural fiber stress strain behavior, we can see, we've tested thousands of single fibers, and one type of behavior that a majority of the fibers that we've tested from flax, from hemp, is this kind of triphasic stress strain behavior. And I won't get into many details, but we have this initial linear elastic behavior followed by some kind of non-linear viscous flow. And then after a bit of time, we get this strain hardening effect where the alignment of those cellulose chains takes place until your ultimate rupture of that particular fiber. And so, this might not be important for a lot of people for a lot of applications, but in terms of how to properly model these fibers so that they can be used in, say, a finite element scenario for design of different structures, this type of information does become important, and that's why we're out to study it and determine its behavior. We've also found that due to the variability of a lot of these natural fibers, especially when we start putting them into composites, the utilization of a statistical modeling approach such as Weibull is somewhat effective. Much like one can assess the strength and the performance of ceramics that have a lot of porosity and a lot of variability in the performance due to the porosity, we've used that same approach with natural fibers, and with fairly good success in terms of matching or being able to predict that performance due to the variability of the fiber structure itself. Another challenge that we've overcome and studied quite a bit is once you form that composite, once you encompass those natural fibers in a resin or a matrix, how do you assess, say, the fiber orientation or voids present, or even fiber volume fraction for that matter? And because the challenge is a lot of your synthetic composites, you can either you dissolve the matrix afterwards to kind of assess the fiber architecture and the fiber volume fraction, or you can perform burn-offs in a controlled environment in order to assess that fiber volume fraction. But with natural fibers, you can't, because then you would degrade the entire material. So we've turned to instrument micro CT, where we're able to X-ray the structure, and we've seen some pretty decent results where we can go in and we can assess voids, we can assess fiber orientation, fiber volume fraction. We can see if there's been, this particular specimen was tested in flexure, and we saw how some shear failure occurred through the thickness of the composite, and we can do a nice assessment of the material without degrading it, say through thermal or type of chemical. We can assess the inside of that composite relatively easily with micro CT. Another aspect we've looked at as a group is the durability, the long-term kind of performance of these composites, and we've used different fatigue testing and modeling approaches to determine things like high cycle fatigue strength of these different types of composites. And we can do so by testing at different temperatures. We can do so by testing at different frequencies. And we've done that and published quite a bit of work on that long-term behavior. And what I can say in general is these biocomposites that we've developed kind of have that break-in period that you see with any type of advanced composite structure. You know, you look at fiberglass reinforced softball bats, for instance. There's kind of this sweet spot where they have this break-in period where you have to damage the structure to a certain degree in order to get, and we're talking on the very much the micro level, you have to induce some damage before you get the ultimate performance of that material in a situation of say, a softball bat. And then after a long period of time or number of cycles that bat has performed, then the properties or the performance starts to tailor off due to the repeated impact of that particular structure. We see several similarities with natural fiber composites as well. Another great aspect is the vibration dampening I talked about earlier. This shows a cantilever beam that was excited based off of flax fiber, and then one versus carbon fiber. And as you can see in the lighter color there is the flax dampens those vibrations much more quickly and dramatically than say in a carbon fiber structure. And that's what sometimes hybridizing these two materials, the benefit that it can provide in your final composite application. Here's just some data that we've kind of gone head to head with a traditional pultruded e-glass and polyester type of composite versus a flax fiber reinforced epoxy sucrosoate type of resin. And in that composite, we had 65% renewable based material. So between the flax and the ESSS, we had some catalyst that was petroleum based. And so by and large, like I said, we were at about 65% bio-based or renewable based. And we had properties that were on par, if not superior, to that of the pultruded e-glass and polyester that is petrochemical based, both in tensile properties as well as flexural properties. and interlaminar shear strength, so the resistance to failure between plies of those fibers. And that's interesting in itself, but then when you compare or look at the density of the two composites, then these gains are even more attractive on a specific basis, because your tensile specific strength or your specific modulus is going to be even higher than your typical or traditional material. I talked a little bit about hybridization and the opportunity to do kind of gain the best of both worlds. You can take a natural fiber such as flax, such as hemp, and you can combine it with carbon fiber, which has a very high strength, high stiffness, and you kind of gain the best of both worlds in terms of strength, in terms of stiffness, as well as reduction of your standard deviation of properties. That'll come out of the carbon fiber. But what you gain out of the natural fiber are things like the vibration dampening, the higher specific strength and specific modulus, as well as the sustainability in terms of utilizing a natural material and less of the synthetically produced reinforcement. And so we've done a lot of studies on hybridizing at different ratios, and then this particular graph is on tensile modulus, and looking at how those properties change going from an all carbon fiber structure to an all flax structure, and looking at basically a linear, close to linear degradation in modulus as you put more flax fiber than carbon fiber into your composite. And that's led me and my students to develop many different types of technology demonstrators. They've been involved with making longboards, bicycles, bicycle helmets, paddle boards, putters, and as well as roofing tiles out of some of these materials. Now that we have a good idea of their properties and performance, actually putting them into applications, testing them, and seeing truly what they're capable of. And that's the exciting part, and why, again, my answer of what's capable for these materials, or what is the outlook for these materials, and I would say it's limitless. I mean, but what is truly or going to be sustainable moving forward, we still have a lot of homework to do. We still have a lot of assessment to do and to understand. And I'll talk about some of those challenges at the end here. With that, kind of using my faculty research hat, I'll kind of bring that discussion to a close, and I'll briefly talk about what I see on the commercial side, or the commercial sector, with my company, C2 Renew. When we started C2 Renew, our goals, or our mission, really was to connect companies in North Dakota, as well as Minnesota, South Dakota, some of our surrounding regions, and partners up in Canada, to help develop ag tech, because our primary economic driver in the state of North Dakota is agriculture. And so how can we complement that, or benefit those that are farming or processing different types of crops? How can we bring them some value add? And as well as create some high-tech jobs for students that want to stay around the area after they're graduated, or maybe we can attract some new engineers and scientists to the region. So who we are is, we are a material designer, formulator, custom compounder, who we develop proprietary formulations based on different types of plastics, thermoplastics, as well as additives and natural fibers, to meet a wide range of engineering specifications. We also do some engineering services to analyze things like mold flow of injection molding grade materials, and see where maybe a weak point in your design based on some of the biocomposite properties that are developed with our material. And we started as a company back in 2012, 2013, going after opportunities that are under the hood, but high volume, so belt guards, say, for skid steers or tractors, handles for tractors, different types of components that might go in inkjet cartridges. But what we quickly learned at that time is that there wasn't a huge cost savings for these companies at that large volume. And so we went through the rigor of being spec'd out on engineering drawings and having in-field testing and certification to be used in these applications. But the interest wasn't quite there from an economic standpoint. And that's when we really switched our gears, or we pivoted and focused on materials that we could create a message with, that consumer-facing products that we wanted to help that company make the product scream green. That's what we always talk about, is you see the biomass, you see that this has more to it than just a traditional plastic. And that's where we've focused most of our attention since that 2014, 2015 time period. And so we've gotten into a lot of different applications, consumer-facing products, packaging, whether it's for air fresheners, rodent repellents, packaging. It could be, we work very closely with Bogo Brush to develop 4 different types of biocomposites for their toothbrush line. We've worked with companies like Dragon Chewer on products, packaging for CBD oil type products. We've also made things like golf tees with Hemp Tees Golf. We've made guitar picks, very simple articles and parts, but at the same time, having that biomass or a particular biomass included into that product allows a better message to be created with their final product. And that's really where we've seen a lot of interest, but there's also been some challenges in that as well, as I'll talk about at the end here. Another area that we've had a good success with is working with 3D printer filament, and a company that we actually share the same building with, 3D Fuel, who manufactures a wide range of different FDM type of materials for 3D printing. One is based off of coffee, and that one we've called Wound Up. One that's based off of residuals from the malting process to make beer, and that one's called Buzzed. With hemp, we've created Entwined. With earthen, we've used waste cotton. And with land filament, this is a very interesting one. We've actually used thermally converted garbage and used that as a filler in PLA to create land filament, which has had quite a bit of success with for 3D printing. Other current product considerations, we're looking a lot at home goods such as bowls, plates, utensils, cosmetic industry, both in containers as well as cosmetic brushes. We're working with a couple different tea manufacturers as well, different avenues there. One particular company approached us to make teas out of coffee, and so we've got bean teas is what they refer to their golf teas as. Coat hangers, clothes hangers, things of that nature as well. But at the end of the day, and I hope to end with some time for Q&A here, we still have some challenges ahead of us. And a lot of this has to do with, again, determining whether these materials that are being created and put out in the wild, as we always say, are they truly sustainable? Are they going to be, in the long run, beneficial, both from that capital standpoint, human standpoint, and planet standpoint, in order to sustain? And some of the challenges that we still have to overcome are a lack in manipulating the surface characteristics so that we can properly bond fibers to different types of resins. We know we have a lack in higher performance, higher temperature performance of natural fibers. So what can we do there to help and improve that? We also have a lack of standards for natural fibers and their composites to properly assess and grade. And in particular, if we look at the woody core of that stalk, where the hurd and the shive come from, things like measuring purity, color, those types of properties are very important for that final compound. And so I'm on several different ASTM committees to help develop standards for natural fibers. I've sat on ASTM D1317 for bast plants and fibers for several years and helped to develop some standards. And I've also now sit on D37.07 for industrial hemp to, again, do very similar standard development especially when it comes to the fiber tensile properties. We need to develop standards, and should those standards be for bundles versus single fibers? And I would argue there's a place for both, because standard to measure tensile properties of single fiber, that might not be important for everybody, especially those in the textile industry who are never going to separate those fibers down to single fibers. They're going to treat them or use them as bundles. And so bundle strength or tensile strength is going to be more important for that type of application. And so we really do need to develop standards for both. And that's what the committees that I've been on are working on at the moment. We know we have a lack in consistent and robust biomass supply chain, especially at C2 Renew. We've had time and time again where, you know, 1 year we can get a good supply of the flax shive or the hemp hurd that we need for our products, but maybe a couple months later we can't get that same quality. We can't get that same supply, and that's very frustrating, especially when we're supplying molders that are molding on a quarterly basis to try and keep enough supply on hand so that we don't interrupt their business flow or their product flow. We also know we've got a lack in the development of robust bio-based polymers, but that's really coming along, and we've made some great strides, especially through work done by my colleagues here in CB2 to develop some fantastic performing bio-based polymers that are going to be really exciting for the future. Lack in development of bio-based additives. So, you know, some of our customers come to us and they ask us, can you make 100% bio-based composite? And my answer is always, probably not. You know, we could maybe get there 96, 98, 99%, but because of the additives either needed for colorant, for improving flexibility or impact performance, we're always going to need some sort of synthetic based additive to get you the performance that you need. And so that could be something that could be investigated further, in my opinion. And then also out in the commercial atmosphere and the consumer facing products, there's still a lack of knowledge when it comes to compostable versus biodegradable, what plastics can do what, and what's appropriate for different applications and different products that we put out into the stores like Target and Walmart. You know, much more emphasis and clarity needs to be put on proper labeling of packages and certain types of materials, because I can have a compostable plastic as a thin film, but the minute that I put it in a thick section product, I can no longer call that as a general compostable material, maybe an industrial compostable material, but because of the wall thickness, that article would need to be shredded first before it could meet those compostability standards, such as ASTM 6400 and so forth. So those are kind of the challenges. Some of the opportunities I see is continued work on hybridization for different structural applications. We can combine bast, hemp, flax with carbon glass for some high performance applications. I also see a huge opportunity for foams and foam composites, specifically to compete against isocyanate. So if you can create a foam that is non-isocyanate reacted, then you have a much better environmentally friendly type of foam product that goes in just about everywhere, whether you're talking about insulative walls, in the cushions of the seats you sit on. There's a ton of opportunities there. Also, I think from a lot of the decortication processes, there's shorter fibers that are created that still have a lot of opportunity for strength in a composite, and we refer to those as kind of this long fiber thermoplastic, or LFT, and those fibers are on the range from anywhere from 1 to 2 inches, where we could do some extrusion compression molding of articles that could have very high performance in comparison to, say, a fiberglass LFT. And then finally, additive manufacturing. We've seen such an explosion and utilization of additive manufacturing. I see this as an opportunity to grow for biocomposites as well as synthetics. And so a lot of opportunities there. as well as challenges. And with that, I thank you for your time and would love to open it up for some Q&A. Again, we can either do this through the chat, or if you feel comfortable, you can unmute yourself and I'll try and answer your question. Thank you.
Thank you very much, Chad. That was really informative. Anyone for questions?
Hi, Chad.
Hello?
I just to say, allowing my video to be on. Hi, this is Abhishek, and I'm from Washington State University. I work with Vikram. So I have a question because, as you have mentioned, that there are very limited standards for fiber reinforced composites, natural fiber reinforced composites. I should rectify myself. So my question is, suppose we have to do some, because you are on the ASTM, you sit on the ASTM board. I'm asking you this. So suppose we have to do some fire testing or fire resistance testing of natural fiber composites. Should we use the CONCAL standard for plastics, or should we use the standard for wood? Which one?
That's a very good question. I would kind of defer, because we don't necessarily have those standards developed for biocomposites yet. I would defer for the application that you're trying to design that material for. Are you creating a biocomposite or a bio-based composite that is going to replace wood for a wood type of application, or are you trying to replace a plastic for a plastic type of application? If it's for the plastic type application, then you would want to use the fire standard for that plastic, whether it's UL 94 or something like that. But if your intention with the development of that material is to go after what's traditionally used, with wood, then you'd want to meet those standards for now. I know, yeah, there's a lot of confusion there, but I would look towards what application are you trying to replace and try and match or meet those standards.
Thank you, Chad.
Yes, you're welcome. Thank you. There's a question in the chat here. Maybe I've missed it, but will you please comment on the max temperature which can be applied during thermoplastic? Okay, so yes, and then specifically he's asking for nylon. So what we've seen is you can sustain about 180 degrees centigrade, maybe 200 degrees centigrade for, during the extrusion process when compounding. So, for that 20, if you're L/D ratio and your compounder of 25 up to 40, you can sustain, 180, 200, maybe even 220 degrees centigrade for that time, that dwell time during that extrusion process. But that kind of limits you, right? That limits you to your polyolefins, your polypropylene, your polyethylene, your PLA, PHA kind of opportunities. So if you want to go into a nylon, then you have to look at a thermally converted type of biomass, maybe like a biochar type of, because if you look at, we've done some pyrolysis or some torrefaction of biomasses, and if you're able to stabilize them at, say, 300 degrees centigrade, then you can introduce them into a wide variety of nylons.
Chad, I have a question for you. You showed a stress strain curve of I'm assuming it's a single fiber. Am I correct?
That's correct. That triphasic behavior, that was a single fiber.
So have you, I'm just wondering, you probably have also tested fiber bundles and how does that, is that very similar in behavior or is it different?
That's a good question. It is quite a bit different, because what you have in a bundle, especially due to the amount of twist, if you have more of a yarn, which is what you typically have with a bundle, you can almost think about, individual fibers are breaking at different points in time, and that creates more of a non-linear behavior. You don't capture that kind of strain hardening effect that I talked about with the single fiber. It's more because of the number of breakage events that goes on in that bundle. You get more of this nonlinear relationship between, almost appears as a little bit of ductility to the fiber, as opposed to a single fiber.
Thank you.
Yep. There's a question here. Have you looked at making paper bags in terms of strength? I have not studied or worked on creating paper products. That's one area that I haven't gone with my research, either university research or with my company. So sorry.
If I may ask another question in the meantime,
Sure.
while we're waiting, you showed a bar graph comparing carbon fiber composite and going towards, as you mix different proportions, towards, I think, a flax fiber composite.
Correct.
Right. What was the process that you used to make the composite? I wasn't sure. Was it pultrusion? Was it extrusion? Injection molded? Or
Yeah.
do you know?
Yeah. Sorry, I didn't mention that. That was actually using a vacuum bagging type of
I
approach.
see.
And what we did is we alternated layers of carbon and flax. Now, another approach is to commingle, which requires obviously, some textile work to be done. But if we found that you get much more better performance if you're able to commingle the flax fiber with the carbon fiber and then create your different layers, both in static properties as well as fatigue. We published recently a paper that shows that the commingling of the fibers is far superior in terms of long-term performance than just alternating layers of carbon flax, or.
Thank you.
Yep.
We have plenty of time if others would like to ask questions.
Chad, just going back to that to Vikram's question, if we were using alternate layers of carbon flax, what was the fiber direction of the layers? Were you using unidirectional or bidirectional?
For that study I showed was unidirectional. And again, you get such a mismatch of of stress from one layer to the next when they're not commingled, and that's what breaks down the composite, or dictates the performance very quickly, is that mismatch when load goes from one fiber layer to the next, and there's such a mismatch. And so in that particular study, yes, we did a unidirectional and alternating layers.
Chad, there are other good questions here in chat. One is, what type of sizing needs to be applied to fibers to make them compatible with common resin systems?
Yeah, that really depends on, you match your compatibilizer with your resin. So for instance, when we're compounding into polypropylene or polyethylene, we usually use a maleic anhydride grafted polypropylene. If it's for polypropylene, we use a maleic anhydride grafted polyethylene. If we're using, our matrix is polyethylene. And we've even made some of our own MAPLA, so maleic anhydride grafted to PLA. When it comes to some of our thermal setting resins, that's where we try some silanes. We found to be somewhat effective, so that you can get that, that bonding of that very hydrophilic surface to that traditionally very hydrophobic matrix. You need that compatibilizer, and it needs to be strategic for the particular polymer that you're working with.
The other question, Chad, is this person said they worked with blended glass and blended carbon fiber with CANAF and found much improved moisture performance. And have you tested for moisture performance and water uptake and mechanical property changes with your carbon fiber natural fiber blend?
That's a good question. We did some moisture studies with a blend of flax fiber, glass fiber in a bio-based thermosetting resin. And we did some durability. We did notice a larger amount of moisture uptake with the addition of the natural fiber, but surprisingly, it wasn't too far off of that of glass. I mean, glass is susceptible to moisture uptake as well. I have not compared it against carbon fiber though, as the question states here, and I've only measured static and dynamic or fatigue performance of those blends of carbon fiber with natural fiber. I haven't done any environmental testing.
Thank you. The next question is, have you done any work with injection molding?
Yes, very much. That's most of the materials that we develop, design, compound for in my private company, C2 Renew, is for injection molding applications. So some of the articles you saw, such as toothbrushes, air freshener, the packaging you saw there for CBD oil, those are all injection molded articles, and that's a tricky balance as well. When we initially developed some of these materials and sent them out to molders, a lot of times they would mold them trying to use traditional parameters, temperature profiles, and they would burn them up pretty quick, and the end result wouldn't be what we thought it would be. And so we learned very quickly that we have to, along with these unique materials that are based off of renewable constituents, we have to educate the molders, and we have to get on the floor and show them, hey, you need to reduce your temperature profile. You maybe have to have a slower velocity on your flow front so that you don't damage the material through shear. And you might have to hold a little bit longer in your tooling so that that material properly sets. Those are all things that we've learned that we need to teach our customers that is different about these materials versus, say, your run and gun polypropylene, polyethylene. You can heat that and jam it in a mold it's very forgiving, whereas some of these materials are not as forgiving during that injection molding process.
The other question, Chad, is, are the fiber supply issues you mentioned improving?
It is. We've seen, I think I mentioned, we've seen more and more decorticators coming online in the US anyway. And so there is some consistency in supply. One large decorticator that has just recently come online for hemp is IND Hemp up in Montana. And I know they are processing at a large scale. I believe Tiger Fiber is another facility in Colorado that supplies a lot of fiber now. And so there's multiple decorticators around the country that are coming online that are definitely helping this issue.
So the next question, Chad, is, have you tried making a molded part with a compounding injection molding machine like the ones made by Kraus Maffei?
Yep. I do have experience with long fiber thermoplastics where you create this, through a plasticator, you create this charge and then use a compression molding or going on to further injection molding. And there are opportunities there. That's one of the points I made in my last slide there is I have not to date used natural fibers in that type of process, but I think there's a huge opportunity for that, because when you start looking at that type of manufacturing process, and the cycle time is very quick, and if you pair that with a natural fiber that has these sustainability characteristics, then you have a very powerful, both from a planet as well as your capital expenditure. You're meeting both of those aspects of sustainability quite well in that scenario.
The next question is, you also mentioned biodegradability versus composting. Are there agencies working on a clear definition between the two, along with requirements for time, exposure, toxins, etc.?
That's something I'm not as involved with in terms of the development of some of those standards and certifications for products. I know there's the BPI certification, there's ASTM committees. Unfortunately, I'm the wrong person to ask on the development if those are getting better or improving. I just know, you know, a decade ago or so, there was a lot of greenwashing. Is like people would say, hey, they put a leaf on their packaging and say, we're green. Well,
Mm.
what does that mean, you know? And I think we're getting better at identifying what that means, but it's taken time and it's going to take more time.
So this is the last question. Which standard did you use to perform the single fiber testing, and if there is a standard?
Again, a standard doesn't exist. So what
Yeah.
we did is we used a piece of equipment that was manufactured in France called a diastron, and it was originally developed to test human hair with different conditioners and shampoos, and so very high precision testing of a natural fiber. But we used that to measure and test the performance of bast fibers.
Well, thank you very much, Chad. That was very enlightening and very informative, and I hope everybody enjoyed it. Thank you very much. Let's just give him a virtual applause, I guess.
All right, thank you,
And
Vic, and
thank
thank you all for attending.
Yeah, and please watch out for other webinars that CB Square would be hosting, and you can go to cb2center.org to get more information. Thank you.